Good morning.
Morning, Horace.
I know you just probably woke up, but I did review the diagram and I'm trying to do as you instructed, not just memorize something, but understand it.
Mm-hmm.
And so what I did was, okay, I know that the proton is in the nucleus,
Mm-hmm.
and I do know that there's a positive charge, and then on the electron, on the neutron, there is a non-positive charge, and that's what holds the atom together. And so the electron orbits around. What I don't understand, see, the electron orbits around. Let's take this example on sodium. I know the proton has 11 elements, but as the electrons orbit around, they have to equal that 11. So you have a 2, 8, and a 1, which equals 11. So that's where that magnetic thing happens. So I
Uh-huh.
don't understand the formula. I went out and got me a statistic calculator that I don't know how to work. So I'm going to have somebody help me with that.
Are
I'm
you
behind, but I'm determined.
are you referring to that 2n squared formula?
Yes. And I think once I learned that, I have a friend that tells me, "Oh, he's good at statistics." He said, I can run you through that."
Horace, that's actually a pretty simple algebraic formula. The letter n stands for whichever orbit you're talking about. So say, for instance, orbit number 2. So you substitute the number 2 for the letter n. So 2 squared is 4. And then multiplied that by 2 is 8. So the second orbit is capable of holding 8. And you can go all the way up. For instance, Horace, gold is element number 79. That means there's 79 protons in the nucleus. There's also 79 electrons orbiting around it, and they are doing so in a very specific pattern, and it's the electron configuration. So in the case of gold, there's more than just 3 or 4 orbits. So let's go ahead and do it. So the third orbit is capable, 3 squared is 9, multiplied by 2 is 18. So the third orbit is capable of 18. The fourth orbit is capable of 32. 4 squared is 16 times 2 is 32. The fifth orbit is capable of holding 50. 5 squared is 25, multiplied by 2 is 50. So here we have 5 orbits. Okay, we don't need, in the case of gold, we don't need 5, but you get the idea. That's how the formula works.
Right.
So in the case of gold, the first 3 orbits, they each have 2, 8, and 18. So far, you have 28 electrons. Now, orbit number 4 contains 32. So when you add that, 32 plus 18, you now have 50 electrons. In the fifth orbit, we already know it's capable of holding 50. However, in the case of gold, there's only 29 electrons left because the first 4 orbits already accounted for 50 of those electrons. The remaining 29 are going to be in orbit number 5. So gold's electron configuration is going to be 2, 8, 18, 32, 29.
Okay, but what's confusing me, because I'm looking at that diagram, and I'm wondering, okay, I see how it's adding up even to the 79 protons. It has to balance each other. So, but I don't know where the numbers. That's the thing I'm trying to understand. And like I said, I had a friend that he said I can try to help you work through the formula. He said same thing you did. He says it's very easy. Once he didn't have time to come show me my calculator how to work it, but he said it's very simple. It's just that I'm not going to say that I'm not smart enough to get it. I'm just going to say that it's going to be a challenge for me, and I believe I can do it once I understand.
Horace, you are smart enough. Don't ever forget that. This is just new to you. That's all. That's all this is. You've never done this before. So don't expect to jump in the deep end of the pool on the first day and swim like you're an Olympic swimmer. It ain't happening. So yes, you're bound to make mistakes. You're bound to trip a little bit here and there. That's to be expected. So
but I'll have that formula down. No, I'll get it.
The gold is 2, 8, 18, 32, 29. That's its electron configuration. And that configuration is what gives gold its yellow color. It's what gives gold its density. That's why gold is so heavy, because of that electron configuration. Gold is also a very soft metal. It can be pounded into any shape, and that's because of the electron configuration. Gold doesn't mix easily with other elements. I mean, it does, but it takes a little effort to do it. That's because of the electron configuration. Another feature of gold is it conducts electricity a heck of a lot more efficiently than copper does.
Okay, another thing I had a question on, I understand that the crust, one of the layers of the earth is called the crust, and that's the part we're standing on, and it has a crack in it. Now, if it has a crack in it and it's part liquid and it moves around, then there's got to be something seeping up. That's what it seems like to me. Something seeping out if it's a crack.
There is. It's called magma or lava. That's the purpose of volcanoes and these cracks in the Earth's surface. They spew out magma. And by the way, everybody that's here right now, there is a definition I want you to know. Molten rock or melted rock is referred to, or it's called magma, when it's inside the earth. The moment it exits out of volcano and starts rolling down the side of a mountain, it changes names to lava. It's the same thing. Lava is on top of the earth, magma is inside the earth, but it's the same thing. And then to give you, now this is a little bit off topic here, Horace, so this isn't going to generate any kind of test question here, but there are objects in the universe. They are stars, but they're not ordinary stars. They're rather unusual. They've already experienced a supernova explosion, And the core of that star, on occasion, somehow miraculously survives that explosion. And the pressures that are at the center of this object are so intense that they have squeezed atoms down to the point where they've actually squashed it down to the point where the star is called a neutron star. It's made up entirely of neutrons. The protons and the electrons have canceled each other out because they've been squeezed together so tightly. So what you have here is a neutron star. This star is so dense, even though it's only about 20 miles across, this neutron star is maybe the size of the greater Los Angeles metropolitan area. And yet it weighs more than our sun. That is dense. Okay.
Recording in progress.
Okay. I left off yesterday talking about layers, and I was referring to this diagram. Any questions on the exam related to layers are going to come from that diagram. So once again, you need to know that the inner core is made up predominantly of iron. The temperatures at the inner core are actually hot enough to liquefy the iron. However, it behaves as if it were a solid. And that has to do with the pressure of the earth sitting on top of it. It's containing it so it doesn't slosh around. It acts as if it's a solid. The outer core is responsible for Earth's magnetic field. Okay. The mantle is the largest of all the layers. It's made up predominantly of rock. Most of that are silicates or granite. Then on the very top of the mantle is another layer that I labeled the asthenosphere. It's the very uppermost portion of the mantle. It acts, metaphorically speaking, it acts like grease under the wheels. It allows the continents on this earth to move across the earth. The crust, which is the thinnest layer, sits on top of this asthenosphere. The crust is cracked in numerous places around the earth. And we've identified approximately 7 large continent-size plates. That's what they're referred to as plates. And then we've identified approximately 24 smaller pieces. So the analogy I was drawing for you is that the surface of Earth, or the crust of Earth, is kind of like the eggshell. It's cracked. The difference is these pieces that make up this shell move over time. We have direct evidence to indicate that North America was at one time sitting over the equator. And evidence of this is actually not hard to see. Here in the United States, once we run out of oil and natural gas, you should take heart in the fact that unless we develop some kind of replacement technology for oil and natural gas, an alternative fuel, our next best option for a fuel source that does not include nuclear reactors is coal. Once we run out of oil and natural gas, everybody, and that's according to all the experts I have read, we are expected to completely deplete our oil and natural gas reserves sometime around the end of this century. Maybe a few years beyond it, but basically right around the beginning of the 22nd century, we should be pretty much out by then. And unless we have developed some kind of technology to adequately replace oil and natural gas, our next best option is coal. Now, coal, oil, and natural gas, some of you may have been told in grade school that oil and natural gas results from the long decaying process of dead dinosaurs. Well, that's only partially true. The biggest contributor to all the oil and natural gas that is found inside the earth, everybody, is not dead dinosaurs, it's dead rainforests. So all of the oil and natural gas and the coal deposits that are located around this earth, that tells us that at one point in the ancient past, that particular area was at one time in the equatorial zone of Earth, because that's where tropical rainforests grow. So the eastern United States, Pennsylvania, Maryland, parts of Virginia, West Virginia, Kentucky, that particular region, this is one of Earth's largest coal deposits on the planet. Just like the Saudi Arabians have oil, we have coal. So that tells us that the eastern United States was at one time a tropical rainforest. And in order to be a tropical rainforest, you have to be in the tropics. So yes, North America was at one time over the equator. The same thing is true with Saudi Arabia. Most of you know that from 6 o'clock news images as a desert, and it is, it's a desert. However, underneath that desert is literally an ocean of oil. So at one time in the distant past, Saudi Arabia was covered completely with a rainforest. Okay. So that's the crust. Now, from this point forward in the lecture, all of the information that I'm going to be giving to you applies only to the crust. We're not talking about the interior of the earth anymore, just the crust. So within the crust, which again we are standing on, there are 3 types of rocks on this earth. And on the study guide there, I'm on number 3 where it says 3 types of rocks. The first one and the most common kind of rock is igneous rock. Igneous rock, and this is a definition you need to know, everybody, so please write this down. Igneous rock forms directly from the solidification of molten magma. Igneous rock forms directly from the solidification of molten magma. There are 2 subcategories of igneous rock: intrinsic and extrinsic. Intrinsic igneous rock is magma that solidified inside the earth. Extrinsic igneous rock is magma that solidified on the surface of earth. And as a result of that, you have 2 completely different types of rock. Why would that be? Let me explain. Suppose you were to make or bake a loaf of bread. Once you made the dough and created the bread, or put the bread dough in a pan and stuck it in the oven, the directions will say to you something like, turn your oven up to 350 degrees and put the bread dough in there for 30 minutes. Well, if you allow magma to cool down inside the earth, it's going to create a rock that is different than magma that cooled outside of the earth. And it's like this: if you put the bread in the oven for 30 minutes, you get a loaf of bread. But if you leave it in the oven for 60 minutes, it's not bread anymore, is it? It's more like a rock. The same analogy applies to the magma. So when magma cools down inside the earth, you can imagine that it's going to take a very long time to cool down because it's inside the earth. And it's going to give up its heat really slowly. And as a result of that, a typical rock that is formed from the solidification of molten magma inside the earth is granite. The Sierra Nevada mountains are Earth's largest piece of exposed granite. That entire mountain range formed inside the earth. The San Andreas fault line pushed it upward out of the ground, and it is continuing to do that even today. It is so successful at it, everybody, that Mount Whitney is the tallest mountain peak in the 48 states. Alaska has a few peaks taller, but in the 48 states, Mount Whitney is the tallest peak. Okay. When magma makes it out a volcano, or as Horace brought up earlier, it escapes through one of these cracks in the Earth's surface, doesn't matter. Because it's on the surface of Earth, it's going to cool down a lot faster. And that is going to end up creating a different kind of rock. So an extrinsic igneous rock is basalt. B-A-S-A-L-T, basalt. Granite is an intrinsic igneous rock. Basalt is an extrinsic igneous rock. Okay. Together, igneous rocks make up 80% by volume of Earth's crust. 80% of Earth's crust is igneous rock. It's either intrinsic or extrinsic, but it's igneous rock. The second type of rock is sedimentary rock. Now, this has a long definition, so I'm going to repeat this. I'm going to say it slowly, but you do need to know this. Sedimentary rock forms from the accumulation, compaction, and cementation of fragmented earth material and organic debris. Once again, sedimentary rock forms from the accumulation, cementation, compaction and cementation of fragmented earth material and organic debris. There are two subcategories to sedimentary rock. It is either clastic or non-clastic. Clastic sedimentary rock is essentially the fragmented earth material. Sand would be an example of a clastic sedimentary rock. It has been fragmented. It is a rock that has been pulverized by the weathering process to the point where it is now sand. Organic debris makes up the non-clastic sedimentary rock. Now, organic debris refers to oil, natural gas, and coal. They are the result of organic debris. So technically speaking, the gasoline that you're putting in your car is a sedimentary rock. An example of a clastic sedimentary rock would be sandstone. We use sandstone as shingles on the roofs of our houses. It is sand that has been accumulated, cemented together, or excuse me, compacted together, and then cemented together to create sandstone. An example of non-clastic sedimentary rock is not just oil and natural gas and coal. It's also limestone. Limestone was at one time a living organism. It was accumulated, it was compacted, it was cemented together to create limestone. All together, everybody, limestone, or excuse me, sedimentary rock makes up 5% of Earth's crust. The third rock category, and here's the definition, these are metamorphic rocks. For those of you who are tech savvy, think about the word morph. What do you do when you morph something? You change it. The definition of a metamorphic rock is that it forms from pre-existing rock through the addition of heat, pressure, and time. Metamorphic rock forms from pre-existing rock with the addition of heat, pressure, and time. Diamonds are metamorphic rocks. They originally started out as carbon, but the carbon over millions of years was subjected to heat and pressure in the interior of Earth. And then, of course, the millions of years being the time, and voila, you change carbon into a diamond. Another common example of a metamorphic rock is marble. Marble was at one time limestone. That limestone was subjected to additional heat, pressure, and time, and it became marble. Okay? Metamorphic rocks make up the remaining 15% of Earth's crust. Okay, so once again, igneous makes up 80%. Sedimentary rock makes up 5%. Metamorphic makes up 15%. And these are the three basic rock types that make up the entire Earth's crust. Okay? So you happen to live next door to the world's largest exposed intrinsic igneous rock. That would be granite. Next time you go hiking in the Sierras, everybody, pay attention to the rock on the trail that you're hiking, because the Sierras are made up of granite. Occasionally, as you hike through the Sierras, you're going to see an exposed piece of granite, which by itself is unremarkable to you. It's, oh, okay, it's just a big rock. What I want you to notice about it is that somewhere in that rock is what looks like a white line. You'd almost think somebody took a big piece of white chalk and drew a line at random across this big, huge piece of granite. Well, obviously it's not chalk. It's quartz. Quartz forms under rather unique conditions. When the magma is inside the earth and it is cooling down, keep in mind that the earth moves, and I don't mean just around the sun, I mean the earth as in the plate tectonics. It moves. So what this does is that as the magma inside the earth solidifies, it is still being subjected to stressful forces that are going to crack that granite, break it up into pieces. And whenever additional magma rises up, it will fill in those cracks. And because of the unique temperature and pressure conditions located in those cracks, it does not form granite, it forms quartz. So if you see a white streak running through a piece of granite, everybody, it's not man-made. It's quartz. If you walk up close enough to it and take a real close look at it, you do not need to be a geologist to see that this is different than the surrounding rock. Some of you are aware of the fact that quartz comes in a variety of colors. Amongst its chemical formulas, I had told you the other day that quartz is made up of the two most common elements in the earth, and that is oxygen and silicon. And that's what quartz is. However, during the process of solidifying, water will become trapped in the quartz as it is forming. And it's the water that gives the quartz its various colors, because if there are any impurities in that water, it will color the quartz. So there's a variety of quartz that is called a rose quartz. The quartz has a somewhat pinkish hue to it. There's quartz that has a green color to it. Its technical name is olivine, but it's quartz of a different color. It's green. So some of you have even gone to, have you ever seen in tourist shops, especially if you visit Pismo Beach and Monterey, in the tourist area, one of the shops that you go into, this is usually just tourists, they have those geodes. You've seen those where it looks like a rock that was sliced in half, and on the interior of the rock, there's all these pretty colors. That rock that you're looking at in the rock store, okay, is actually solidified molten magma. It was ejected out of a volcano, and it was ejected as a blob of magma. So you have this big, huge blob of magma that is probably the size of a large beach ball. And it has been ejected out of the volcano at hundreds of miles an hour. As this blob of magma moves through the air at that speed, everybody, the wind pressure is going to push inward at the middle of that blob. So you have this blob of magma, and air pressure is going to push in this direction, and the blob of magma is going to fold over that pocket of air. And in the process, it's going to trap in it whatever water vapor happened to be in the air at the time of the eruption. And depending on what impurities were in that water, you get your various colors. A common one, most of you have seen this before, is a purplish type of color. Amethyst comes to mind because that's how amethyst is formed. It was formed in a blob of magma that was ejected out of a volcano. It formed a pocket of air as it was moving through the air. It solidified in such a way that the interior of that rock was hollow. And then some geologist finds it, cuts it in half, and then you have all those pretty colors. And they sell it to you at the rock store for hundreds of dollars. What a scam, huh? You're buying a rock for $300. Okay. Now, there is another handout that I gave you, and correct me if I'm wrong. If I didn't send it to you, I will. But anyway, do you guys have a handout that looks like this?
I'm looking through my papers.
I have it.
Okay, it says mineral group on the right side, and on the left side, there's some definitions with the 8 most common elements. I am not going to ask you to memorize all this information for the sake of the test. You don't have to, because you got the handouts and you don't have to really memorize it. But do you remember me telling you earlier that of the 92 naturally occurring elements, only 8 of them are found in any sizable quantity? Well, here's the 8 most common elements in the earth. And once again, a reminder, we are talking about the crust. So the 2 most common are silicon and oxygen. And if you take a look at those percent numbers, everybody, what that's telling you is that silicon and oxygen make up nearly 3/4 of Earth's crust. So there's a lot of granite and a lot of quartz in the Earth's crust. And then you have aluminum, iron, calcium, sodium, potassium, and magnesium. Aluminum and iron you're all familiar with. It's a metal. It's one of the reasons why our industrial infrastructure is built on iron. It's common. You can dig it up out of the ground almost anywhere. The last four, calcium, sodium, potassium, and magnesium, are salts. Okay? During the time of the ancient Romans, everybody, Julius Caesar used to pay his soldiers in salt. That was a common form of currency back then. And there's an old saying that has survived the 2,000 years since the Roman Empire. And that is that when you make a comment that this man is worth his salt, that's where it originates from. Because in the time of Julius Caesar, salt was a form of currency. It's also what makes up a large part of us. You've heard, no doubt, that we are mostly water and a few pounds of chemicals. And that's true. That's what we are. However, if you break down those chemicals, you find out that most of them are salts of one kind or another. Sodium, potassium, calcium, magnesium, phosphorus is another one. These are salts. We are the salt of the earth. These are also, by the way, plant nutrients. Plants have to eat just like humans do. They just eat in a different form, that's all. The right-hand side of that diagram are the mineral groups. Don't worry about memorizing them. I just put them down there for reference. You can see what kind of rocks are considered what kind of mineral group. On exam number 3, the questions that are going to be related to this handout, I'm going to give them to you right now. You're going to need to know that mineral group number 1, native elements, of the 8 mineral groups listed there, everybody, native elements are the only ones found in the earth in their pure chemical form. So when you dig gold up out of the ground, it is a native element. And what that means is, everybody, is that chemically speaking, it's just gold. It's not gold oxide. It's not gold chloride. It's just gold. Yes, it's embedded in rock, but chemically speaking, it's just gold. Copper is another native element. When you dig it up out of the ground, it's just copper. Silver is a native element. Okay, so you need to know that native elements are the only ones found in their pure form. The second one of these mineral groups that's going to generate a question is the last one, number 8, silicates. It's the largest of the 8 in terms of how much stuff is in the crust of the earth. Most of it is classified a silicate. So it's the largest in terms of volume of those 8 mineral groups. So that's the questions on the exam are going to be related to native elements and the silicates, okay? Examples of the silicates are just listed there for your reference. You're not going to need to memorize them for the test or anything, but some of you have a preference for some of these stones. I personally like opals myself, but you know, people have their own preferences. Personally, I enjoy the semi-precious stones more than I do the diamonds. So anyway, those are the only two questions, well, the only two subjects that are going to show up from this handout here, okay? Also, please notice in the upper left-hand corner, there's a definition of an element and a mineral. That's also going to show up as an exam question, okay? Now,
Can you print that? I mean, send that, because I don't seem to find it when you get a chance, please. The diagram. Well, thank you.
all right. But the rest of you got it, right?
I did not get it either.
No, there's like 5 of us in the chat that did not
Yeah.
get it.
It'll be
All
there.
right. All right. Well, you can replay the recording later so that you don't miss anything. But yes, I'll send out the mineral groups again.
Thank you.
So what I want to do now is I want to close with a few comments. I received some emails from students who were concerned about their grade, and it's not that they're failing. They were interested in salvaging their grade from exam 2. So to put it nicely, they were asking me if there's the possibility of extra credit to help make up for exam 2, okay? And I've given it some thought, and what I am considering, everybody, is if I put extra credit on exam number 3, I was going to see about making it related to the combining of elements. And that explanation is in the handout that looks like this. Okay. So as far as the extra credit goes, in addition to sending you the mineral group outline, I'll tell you what I'm going to do. I am going to send you some problems to solve, and it's going to be the extra credit on exam 3. And it's going to involve the combination of 2 different ions. Do you remember me telling you that sodium has a +1 above it? Whenever you see a plus or a minus sign above the symbol of an element, that element is now an ion. What is the meaning of an ion? An ion merely means that that element has an electrical charge to it. That's all an ion is. So for instance, sodium is sodium. That doesn't change. But you have the element sodium, which has 11 protons and 11 electrons around it. So it does not have an electrical charge because you have 11 negative electrons and 11 positive protons. They cancel each other out electrically speaking, so they're neutral. When a sodium atom loses one of its electrons, it now only has 10 electrons, but it still has 11 positive protons. So its net electrical charge is +1, and it's an ion. So if I ask you on the test, if I give you a list of elements and I ask you to identify which one of these 5 elements is an ion, what you are looking for is a number above the symbol. You don't care if it's a positive or a negative, just a number above the symbol means it's an ion. So there'll be 4 elements with no numbers above them and 1 element with a number above it. That's the ion. Sodium has a +1 electrical charge to it. The sodium ion does. Chlorine, on the other hand, the example I gave yesterday, has a -1 electrical charge associated with it. So in the example that I gave in the handout, you can in fact combine sodium and chlorine together because they are opposite charges. One's positive, one is negative. But they are also both, one is a +1, the other one is a -1. So the charges are going to cancel each other out. And the 2 elements are going to combine with each other on a 1-to-1 ratio, 1 sodium with 1 chlorine. And you get sodium chloride, which is common table salt. So I will send out a type of, and I'll explain it further, but I'm going to send out to you some problem solving about combining ions. There's going to be 3 rules that you have to follow when you combine them, and I'll put these rules on the handout. First, rule number 1, only opposites mix. So sodium is a +1 ion. Potassium happens to also be a +1 ion. You cannot mix sodium and potassium because they have the same electrical charge. You can mix them with oxygen because oxygen has a negative charge to it. Oxygen has a -2 charge. So you can combine it with sodium. Now, here's a little bit of critical thinking, everybody. Sodium is +1. Oxygen is -2. That means you're going to need 2 sodiums to cancel out that 1 oxygen. So the formula is going to be Na subscript 2, because it took 2 sodiums, and then just O for oxygen, no subscript. Na2O. You can do the same thing with potassium because it's positive, oxygen is negative. Potassium is +1, oxygen is -2. Just like sodium, it's going to take 2 potassiums to cancel out 1 oxygen. So the formula is going to be K2O. Hydrogen has a +1 electrical charge to it. Oxygen has a -2 charge to it. So it's going to take 2 hydrogens to cancel out 1 oxygen. So you're going to end up with H2O. So I'm going to send you some practice problems on doing just that. And that is going to be the extra credit on exam 3. Okay? So I will be sending you the handouts later this afternoon as well as the recording. Okay? Keep in mind the class comes to an end next week. So we do have to finish the material by Wednesday at the latest. So Tuesday and Wednesday are going to be a little bit busy because on Wednesday, I would also like to devote some of the time to going over the exam itself. Okay? Just like I did for exam 2, I will go over what kind of questions you can expect to see and point out what specifically you're going to need to know. Okay? So unless anybody has any questions, I will see everybody next Tuesday.
Thank you.
Okay. Bye-bye, everybody.
Recording stopped.
I want to tell you something really funny.
Yeah.
So when you're talking about the rocks, and there was a huge gem show every year when I lived in Tucson,
Uh-huh.
and they would have these humongous, for like thousands and thousands of dollars, like as tall as me,
Uh-huh.
of the rocks that you're talking about with the purple.
Yeah.
So it just made me think of that.
Yeah. It's you're only paying that much money because of the physical size and the effort it took to bring it into that rock shop because it's big.
Yeah.
So that's what you're paying all that money for, not necessarily because the rock in those pretty colors are, in some way going to make you a millionaire.
Are
because
they
they're
worth
not.
anything? No.
Yeah, because if they really were that expensive, trust me, the guy who dug this up out of the ground
Would have sold it.
Yeah.
Yes. Yes.
But yeah, they're nice to look at. They're curious. That's all. I personally have never purchased one, but those kind of rocks, believe it or not, are common in Central America and parts of Venezuela and things, because remember, South America is crashing into North America and it's creating a lot of volcanic activity. So a lot of those rocks you see at the rock shop come from Central America.
At the gem shows, you mean?
Yeah.
Yeah.
And the same thing would be true in places like Indonesia, Papua New Guinea, because those Australia is crashing into Southeast Asia. The collision is creating Indonesia and all the rest of those islands. And there's a lot of this particular volcanic rock found in that region. So that's typically where they come from. There's other places, but those are the two most common.
Very, very interesting.
Mm-hmm.
But
Okay.
I just wanted to share that because I was like, oh, it made me think of years ago.
Yeah, yeah. The next time you're in Arizona, something curious you could get the kids to do. You're aware of Meteor Crater in Arizona?
Yes, I think so.
Okay. Fragments of that meteor are scattered all about the desert. And a lot of them have been picked up and discovered already, but there's still quite a number of smaller fragments scattered about the desert. And if you look long enough, you'll eventually find one. And they stand out against the desert landscape because they're black in appearance and they're very shiny looking. They almost look like somebody polished them. And what that has to do, the shininess comes from the heat treatment that the rock experienced as it was passing through our atmosphere. Because it hit the earth probably doing 50,000 miles an hour. And so when it was passing through our atmosphere, it generated a lot of heat. And so it gave the rock a bit of a glossy appearance. These little rocks I'm talking about are probably not maybe the size of your thumbnail, slightly bigger. They're called tektites. And it's the reason you might want to send your kids out. I mean, it's just interesting. It's curious. It's a piece of an asteroid. You know, how cool is that?
Yeah, exactly.
Yeah. So if you're ever down there again, keep an eye out for it. And just also keep in mind too, the Meteor Crater in Arizona is 1 mile wide. The rock that made that 1 mile wide crater was probably only 150 feet across. That's how much energy it hit the earth with. When you look up at the moon on a clear night, everyone, take a look at the southern region of the moon. If you happen to have even a cheap pair of binoculars, you can see that on the near the southern pole of the moon, there's what appears to be a crater, a large one.
Yeah.
And it's a 600-mile wide crater. So whatever hit the moon to create that crater was absolutely huge. And it's visible with the naked eye from you standing here on the surface of Earth.
Mm-hmm.
And so if you look up at the moon, it's in the southern region and it's pretty large. You can't miss it. So yeah, how big was that object and how fast was it traveling? Yeah. So we believe Earth has many craters on it. The only difference is you can't see them because of the weathering process. So when one of these big, huge rocks hits the Earth, the weathering process is eventually over time going to erase evidence of its existence. So this is why Earth does not look like the moon. We have weather. The moon does not. So for instance, the footsteps that Neil Armstrong left on the moon in 1969, those footprints are still there, completely undisturbed, and they will continue to be there for millions of years without any disturbance. There's no weather on the moon. So the craters last forever and ever and ever. That's how astronomers can tell if a landscape that they are looking at through their telescopes is new or old. If it's new, there's not very many craters on the surface because there's not been enough time for impacts to occur. If they see a lot of craters on the surface, it's an old landscape. It also tells them if there's a lot of craters on the surface, there's no weathering process and there's no plate tectonics. In other words, there's no volcanoes to erase the crater. So if we see a landscape that looks smoothed over, it's a new landscape. And there's only two things that could have created it: a weathering process or volcanic activity. So that's how we can tell, for instance, Mars is either an old or a new landscape, or any other object in our solar system. We have a good idea of how either old or young it is. Okay. I'll see all you guys tomorrow, Tuesday.
I have a quick question before you take off.
Yeah,
So as far as the extra credit goes on the exam, if we don't necessarily need it, do we just leave it blank?
yes,
Okay,
you're not required to fill it out.
okay, I just wanted to make sure.
Yeah.
I'm, okay,
No.
all right.
Okay. Yeah. I'll probably send it out next Wednesday evening so that you can all have it turned in the next day by Thursday, and then hopefully input to the computer by Friday. Sure. Okay. Bye-bye.